First thing we're going to be doing is continuing from last time. We've got sequences. And what I've written down here are 3 questions, very similar to your homework questions. We're going to finish, and today we're going to, this is the end of it, we're going to finish, how do you create formula for a sequence? Yesterday I told you that there were 3 main families of sequences in which you are typically going to meet, and that there's ways to figuring out what the formula are for 2 of them. Whoa, for 2 of them. But the third one is a kind of catch-all. That's, you know, everybody else is out there kind of sequence. So I'm going to mute you. So if you want to answer a question, remember to hit the spacebar. I'll keep the background sound gone. One of these is geometric. One of these is arithmetic sequence. And one of these is just a general sequence. So I guess the first thing you have to be able to do is identify what kind of sequence you've got, because won't that decide how you're going to, you know, proceed from that point onwards. Right. Here's number 1. Geometric, arithmetic, or is it one of those one-off general ones? What have you got here?
Geometric.
I like your answer. You want to tell some of the others in the class what led you to that? Is correct.
Because it's negative, positive, and negative, positive.
So so all geometric series do that, or is there more to the geometric sequence than just that? You're correct, they do go plus minus.
Oh, well, that was the first indication.
Yeah, and what kind of pushed you over the edge? Because actually, that second question also goes plus and negative. Right, this number 3 goes plus and negative, but the number 3 is not a geometric. So,
okay, I didn't know that.
So what else is going on? You're right about geometric. So how would we test for geometric if we decide?
There's a factor of 2/3 being
right. So you basically, you remember yesterday we said, look, take the second term divided by the first. And if it's a geometric, shouldn't that be the same every time? So it's going to be pretty messy because the numbers don't work out well. But that's 8/3 divided by -4. And I believe that gets you -2/3. And you're going to trust me in this, but if I took this guy and divided it by that, it would be the same. If I took this guy and multiplied it by that, it would be the same. So whenever you get the same multiplication, that's a geometric, right? And what's the common ratio? Well, if you take the second term and divide it by the first and simplify it down, you've got it. Now, if you're going to do a geometric, right, so this is going to be my answer to the first one. There is a formula that we gave you that works. In fact, I believe I proved it to you. Can you remember what that formula is? And then we'll plug the numbers
in. Is that the AR to the power n-1, right?
That is the one. And A is the first term. And R is the common ratio. And so we're going to be looking at -4 times -2/3 to the n-1. And it's not very pretty, but that will actually, that works, right? That will get you every single term in the sequence here, right? If I wanted to know the 10th one, which I don't, but if I did want to know it, when I just make that 9, right? 10 take away 1 and do some horrible calculation. But now I'm going to talk about style points. That's correct. That is the formula for this sequence, this geometric sequence, but it can be made to look prettier, right? Now, in some cases, it can. In this case, I'm going to try. It's going to be -4, that guy on the top, and that guy on the bottom. Right, that's allowed, agreed? You can take a fraction that's raised to a power and split it into 2, top power, bottom power. Now, don't expect to have to do this much. This is kind of rare, but I want to show you it happening. If you take this -2 to the power of n-1, you can actually split it up like this. Okay. Now it gets a little bit trickier here. That -4 is basically the same thing as -1 times 4. Agreed? That's just another way of looking at it. Then that -1 could join this power and get one more power. And so I get that. Is there another way of thinking about 4 in terms of 2? Can you think of another way to write down 4 using 2?
2 squared.
2 squared. So I'm going to put a 2 squared here. Probably don't need this line, but I don't want to do too much. We get that. And can't that 2 squared be multiplied by this and essentially add to the power? So the final result to this question ends up being that guy. That's what we started with, and that's what it became. It's slightly nicer, would you agree? Slightly nicer. No, Jeremy doesn't think it's nicer. Well, I think it's nicer, right? But in general, you don't need to be too focused on that. But I did want to show you this because you might come across a situation in the future, and if you do more advanced math, where we wouldn't leave that. We would try and make it look pretty. So at least I want you to say, I've seen how you do it. Don't you kind of break it apart into little bits and then try and put them together in a slightly different order. That's essentially what I did there. But not a common thing, so don't get too worried. Right, second guy. I'll cover this up so it doesn't distract us. Arithmetic, geometric, or just one of those one-off general. What you got here?
Arithmetic.
Okay, correct. Tell me why.
You're adding by 4 each time.
Perfect. Right, that was a lot easier. Would you agree it's maybe easier to recognize an arithmetic than it is to recognize a geometric? Because adding's pretty easy to do in your head, right? Multiplying by weird fractions is not. So if you want to do this one, you need to know 2 things. You need to know A, which is the first number, and you need to know a guy called D, which is a common difference. And in this case, aren't you just adding 4? So I'm doing it in my head. If you wanted to see that as a calculation, wouldn't it be the second guy take away the first, not the second guy divided by the first? And so put it here. Can anyone remember the formula from yesterday using A and D that gives you every arithmetic sequence in the universe?
Wasn't it A plus the quantity of n minus 1 times D?
That's the guy. In this case, you've got a 3 and you've got an n minus 1 times 4. Now, when you do geometric sequences, you very often just leave them, in the ugly format that they come, unless, you're encouraged to do it. But in an arithmetic, you never leave it like that. Would you agree that's not really good math looking, right? It doesn't have a clean feel to it. So what you would always do in this case is distribute the 4. So 4 times n, 4 times that, and then combine the numbers. And that is your guy, isn't it? That is your formula for any term in that. And if I wanted to check, couldn't I say, okay, the 4th number is 16, right? Would you agree that 1, 2, 3, the 4th number should be 16? And I could check that that formula works by finding the 4th term. And 4 times 4 take away 1 is exactly what it should be. And isn't that a verification? I could have, but it'd be much uglier. Couldn't have checked this formula here by picking, where is it? 1, 2. By picking the 4th number and proving that you got that. I don't want to do it, it's messy as heck, but it would work. You trust me, it would work. Well, to finish with, I picked this guy. And he's very like question, in case you come to it, is very like question 12 in the homework. Now this one is not an arithmetic. I think you can tell. Would you agree you're not adding the same amount to each term? So it's not arithmetic. If you divide this guy by that, you'll get a fraction. But if you divide this guy by that, you get a totally different fraction. So that means it's not geometric, right? Isn't it the same ratio each time you do the division? So when you're stuck with something as ugly as this one is, although in my mind it's kind of elegant, all bets are off. You just have to figure out some way of coming up with a formula for it, right? So here's one approach. One gets you that, second term is that, third term is that, fourth term is that, fifth term is that. All I need to do is figure out what the nth term is, and I've got my formula, right? Well, there's an awful lot going on. I wouldn't try and do it in one go. What I'm going to do is break it into little pieces and then put the pieces together to get my formula. So here is where my formula is going to go. First thing I'm going to notice is, do you notice it goes plus, minus, plus, minus, plus, minus? If you want to create alternating plus minuses, you're going to use -1 to the n, or you're going to use -1 to the n plus 1. Now, the reason that there are two versions, one of these starts with a positive, and then you go negative, then you go positive. And the other, you start with a negative number, and then you go positive, right? So it's all to do with the who goes first kind of thing. Now, if you plug in 1 here, you get -1 to the 1, which is -1. So that makes the first term negative. If you plug 1 in here, you get -1, 1 plus 1 is squared, you get +1. So this one here alternates, but you start with a positive. And this one here, it alternates and starts with a negative. In this case, didn't we start with a positive a 6? And because I know this one will generate that sequence, I now have that guy. Now, all I've done right now is figured a way to make all these pluses and minuses up. And I'm going to focus on the top. But I don't care that it's plus or minus anymore. In fact, I'm going to ignore that. I'm going to just pretend they're all positive. And I try and hopefully see something going on. And we should have. 1, 4, 9, 16, 25. Can you see what's the heck's going on here? Can you see a pattern?
Is that every number just getting square up, right?
Yeah. So if I wanted the nth number, wouldn't I just get n squared? Do you see where that came from? Now let's focus on the last piece of the puzzles. Do you see how I'm not doing the whole question? I'm doing a bit of the question. How do I make the plus minus happen? How do I figure out just what's on the top? Now, how do I figure out, right, what's going to happen in the bottom? Well, the first answer is a 6. The second answer needs to be a 7. The third answer needs to be an 8, and so on and so on. Right? What is the connection between the position 3 and the bottom number 8? Right? Position 4 and the bottom number. I apologize, that's a 9. Yeah, that's better, right? What is the connection between these? How do you do that?
N plus 5.
Are you all comfortable with that word, n plus 5? Well, just stick an a in at the front and you are done. So for that particular sequence, would you agree it's not really like there's a formula when it's geometric, there's a formula when it's arithmetic? Isn't this one just flying by the seat of your pants, right? Just trying to figure out, can I figure out what the bits that are made from it are equal to as a formula? And that's basically us up to question 12. Our next thing we're going to look at is how to graph a sequence. So you're going to be given a formula. Let me pick one. I think I've already got one set up, so let me make sure I make my life easy by picking that. Yeah. So let's have a sequence, and it's going to be n plus 1 over n cubed plus n, right? And we're going to be asked in our homework to do two major things. One is we're going to be asked to create a table rounded off to 4 decimal places. So that means we don't need to worry about making everybody an exact value now, right? We're just going to round them off. And we're meant to be doing the table I'm looking at looks something like this. It goes n, and then it's the function, and it goes 1, 2, excuse the untidiness. And basically, isn't that us just writing down the first 10 terms of this sequence, but we're just putting it in a table format? Agreed? Just the first 10 terms. Now, I'm sure I did. Didn't we show you yesterday that you can let your calculator take a lot of the heavy duty work out of it, right? Now, we're being asked to do these answers to 4 decimal places, which is fine, but we have to kind of tweak how this works in our calculator. So I'm going to go in and do y equals. I'm going to put a bracket and call that x plus 1, close bracket. I'm then going to divide, and on the bottom I'm going to do x cubed, and I'm going to do plus x, finished. Then I'm going to do the table setup. Well, actually, I don't need to, because if I did it yesterday, which I did, it's still going to be there, right? So it's already set up. In case you didn't catch it yesterday, hit the second button window, and you get into table setup. And just make sure that starts at 1 and that goes up in 1. But most importantly, just make that guy there. Make sure he says ask. Right. And if you've done that, just leave it alone, because that's how you're going to use it for a lot of the time. Now I'm now going to go second table, and I'll just clear out some old stuff, and I'll just go 1 and 2 and 3 and 4, 5 and 6 and 7 and 8 and 9 and 10. And I changed my mind. I thought I needed to show you how to get more accuracy out of it, but since this is 4 decimal places, would you agree all those guys in front of us are good to 5 decimal places? So don't I just need to round them up? So that answer there is going to be 1. That's going to be 0.3. And this one is going to be 0.1, 2, 3, 4, right, and so on. Nothing too difficult there, isn't it? Just time consuming, right? Set up your calculator, do the first term. But how do I graph that? Well, if I wanted to do it by hand, which I don't, wouldn't I draw just a set of axes? Wouldn't I go 1, 2, 3, 4, 5, and so on? And that axis would represent the term. And then the vertical axis would basically be the value of the function an. It looks like here 0.2, 0.4, 0.6, 0.8, 10. There's 1, there's 0.2, 0.4, 0.6, 0.8. And I would simply just do, at 1, the answer is 1. A2, the answer is 0.3. A3, it's about 0.13, which is about there, and then put that one, and that one, and that one, and that one. Do you see that your graph is actually just a set of dots, isn't it? Almost like coordinates, isn't it? Like 1, 1, 2, 0.3. That's a lot of work. Wouldn't it be at least nice if we could do the graphing part without having to, do all this, setting up a grid and guesstimating the value? So I'm going to switch it over now to Desmos, and we'll show you how Desmos can do the graphing part, at least for us. Yeah, it's ready. Okay. Where's Desmos? Oh, here it is. There. Now, you don't need to do it this way, but once you've set this up, it's a lot easier to do the next ones, right? Just so capital N equals 10 because I've got 10 guys here, right? Right, my table of 10 values. This is a function, I'm calling it AX, and it's basically, isn't that my n plus 1 over n cubed plus n, right? You notice I've used x's, but that's what that is. Then you do this funny little thing here, bracket n comma an. That's actually what's plotting the dots. If I put this guy in, that blue thing is actually what that function looks like in terms of x. But if you click on it, you can make it go away. And then the last little bit is this little tricky piece down here. Little n equals 1, 2, 3 dots to n. So if I make n 100 and I click off this, you can't really see it because the scale shrinks it down, but haven't actually got the first 100 ones drawn. If you don't like your scale, hit the little graph symbol, go to the y value, and just put in something like maybe negative 0.1, and on this side, maybe just put in 1. In fact, maybe put in nothing, 0.1. There, that's a little bit clearer. Do you get a better idea of what the sequence looks like? Although I might lose a couple of terms up the top. There they are, can you see them now? So what does WebAssign do? Well, let's show you what that question would look like in a WebAssign homework. So I'm going to go in and open a different window. There we go. Now, stop sharing for a second so I can go back in. And it looks like this. Right, so when you put all the numbers in that table that we had, for instance, you put in a 1 here and whatever it happened to be, that's their function. And then all you need to do is pick whichever one of those guys looks like yours. Now, the one I did isn't actually this equation, right? But can you imagine if you did this one of those 4 pictures would match. And you'd say, let's pretend it was that one, right? So WebAssign doesn't ask you to go into WebAssign and plot it. Doesn't WebAssign just show you the finished result and you pick which one looks like your finished result? Now, are we cool so far? Right. Now, they introduce here, and I want to talk a lot more about this in a minute, is does this sequence have a limit? Can you remember in 151, we did for the first couple of weeks, we spent a lot of time on calculating limits. Isn't the limit of a sequence then, what is the value as n tends to infinity of whatever the function happens to be? And if it levels off horizontally, isn't that a limit? And if it zooms off to infinity like a rocket, and we say it diverges. So, or no, it doesn't have a limit. Are we good with that type of question where you fill in a table and then you can use Desmos to help you sketch it? By the way, although I haven't done a really good job on this, wouldn't the limit of this sequence, would it be reasonable to assume that the limit was 0? You can kind of see it. Let's talk about how to find limits, not by graphing them and doing plots, because that takes forever, right? Doesn't that take forever, right? How do you find limits of sequences then? That's the next topic. Well, the good news is you already know how to do it. You may have got a bit rusty, but you've seen it before. If you want to find the limit of any sequence, right? So I guess it would look like that. There are going to be 2 things. Now let's rephrase it. There are going to be 3 things that can happen. Couldn't the limit be a number like 1? or 42 or 0, right? And when that happens, we will say that the sequence converges, in this case, oh, let's make it 11, right? So the series converges to 11. That's one thing that can happen. You could do the limit of the sequence and the answer ends up being infinity, right? Can you imagine that would be shooting off the universe? When that happens, you will just say that the sequence diverges, right? You don't need to go into any details. You just click the little circle that says diverges. Now, I said there was 3 possibilities because I just thought of one more. And this is an example of it. Right, here's the sequence. If you write that sequence down, this is what you get for eternity. Would you agree that that sequence has no limit? Doesn't it bounce between 2 numbers, right? It has no limit. Would you also agree that it's not infinite? The numbers are 1 or -1, right? None of them are infinite. In that case, we also call it diverges. So we don't care if the reason it doesn't work is because it's infinitely big, or the reason it doesn't work is because it doesn't go anywhere, right? It jumps around randomly or whatever. Another example of this type would be maybe this one. This one also diverges. If you calculated that sequence, wouldn't your answers just bounce between 1 and -1 for eternity? It would never level off anywhere, right? Sine of 42, sine of 43, sine of 49, sine of 1,000,000, sine of 1,000,001. The sine function is sinusoidal, right? It goes everywhere. So how do we calculate limits? Let's show you. There are a number of techniques. The first one is called brute force. The second method that we often apply is divide the numerator and the denominator by some power of n, like n cubed. The third technique is a guy that you haven't met for a while, is L'Hopital. And the fourth one, which you've never seen, so this is a new one for you probably, for most of you, is the relative rate of increase. So let's show you an example of each one of these methods being used to find the limit of a sequence, if it does exist. Suppose I had a sequence and it was 4 over n cubed. And I wanted to know its limit. So I'm trying to find the limit as n tends to infinity of 4 over n cubed. The method called brute force basically says, make n infinite and see what you get. Well, let's see what happens. Don't you get 4 over infinity cubed? But isn't infinity times itself still infinite? And what does 4 divided by an infinitely large number get you as a limit?
0.
0. That's an example of brute force. Show you another one. Still on brute force. Suppose I had a sequence which was the inverse tan of n squared, right? Imagine that was my sequence. Now, if you do brute force, you're going to get the inverse tan of infinity squared. And that's going to become the inverse tan of infinity. But the inverse tan of infinity is not infinity. Right? The inverse tan of infinity is what angle in radians would you get an infinite tan? Right? You know how the tan function zooms up the way. what value makes that happen? What angle in radians
Is
makes,
that the 90 degree?
and what do you call that in radians?
The 1/2, right? Oh,
Yeah.
pi over half.
Yeah, a half is right. Half pi or pi over 2. So that one converges. Let me do one last one. If you plug in infinity here, would you agree that infinity squared is infinite, and then you add some more infinite? Isn't the answer just going to be infinite? In this case, you would just say it diverges. Right? We don't care that it's the reason it diverges is the answer is infinite. We just say diverges. Do you recognize this technique of just plugging in infinity and the result tells you if it converges to a number or 0, or it just diverges? So far, so good? Are we good? Okay, that's basically number 1. Let's do number 2 then, the method 2. And that's the one that I've called divide the numerator and denominator by a pair. Now, you would use it in situations where you have a rational function and the top and bottom are polynomials. So if you get a question that looks like that, right, a rational function, a fraction function, and the top is full of n cubes and n squareds, and the bottom's full of n cubes and n squareds, right? Things that look like that. You want to find what the limit of that sequence is. Technique I'm going to use is you divide the top and bottom by the same power. Now, what power of n do you use? Well, the highest power on the top is n squared, and thankfully the highest power on the bottom here is also n squared. So when they are the same, you don't have a choice. You multiply both the top and bottom by n squared. No matter what situation you've got, these two guys must be the same. And this divide by n squared is essentially multiplying by 1 over n squared, but that looks weird. So what does our fella become when you do that? Well, you take each term in turn and divide it, and that gets you 1. Divide that guy, and you get 1 over n squared. Divide this guy, you get 4. And divide these, and you get 1 over n. Now, once you've done the divide top and bottom by n squared, n cubed, it's always a power of n of some kind. You can then finish by doing the brute force part. You just do 1 plus 1 over infinity squared on the top, and 4 plus 1 over infinity on the bottom. Okay. Isn't 1 over infinity squared just 0? And isn't 1 over infinity also just 0? So what you're left with is a quarter. So this sequence has a limit of a quarter. If you did it on Desmos, and can you imagine that little dotted line there was a quarter, your sequence might look something like this. You get that kind of leveling off effect, right? Like a horizontal asymptote. Does this look familiar, even although it's got n's and not x's? It's the same kind of thing you did way back in Calc 1, where you're trying to find the limit of x squared plus 1 over 4x squared plus x, right? It's essentially the same technique.
What did you call this?
This one, this is my own made-up name for it, because I don't think it's got a name. Divide the numerator and denominator by a power of n. Right?
Okay.
That's one. Okay. Now, let's do another one. How about this one? Because there's 3 situations I want you to see. We're going to do 4n cubed plus 2 over 2n squared plus n. So I'm wanting to find the limit as n tends to infinity. And I have a 4n cubed plus 2, and I have a 2n squared plus n. And I'm going to use this divide top and bottom technique. Okay. I have a choice. Divide the top and bottom by n squared, or divide the top and bottom by n cubed. I must make it the same, right? I can't make one of them a cube and the other a square, right? Not allowed, right? Mathematically, you can't get away with that. So here's your rule. Pick the smaller of the two choices. Right? So that's what I'm going to do. I'm going to divide top and bottom by n squared. Now, you might look at other videos or PDFs or tutoring online, and they will tell you to divide top and bottom by n cubed. That works as well, but I don't like doing it that way. I think the smaller one tends to, in most situations, make the math easier to understand. At least in my brain it does. So let's see what we get. We're going to get the limit as n tends to infinity. That guy becomes 4n, and that guy becomes 2 over n squared. That guy becomes the number 2, and that guy becomes 1 over n squared. And that guy becomes 1 over n, actually. And then I finish by doing my brute force thing. 4 lots of infinity plus 2 over infinity, and 2 plus 1 over infinity. 4 times infinity is still infinitely large. 2 over infinity is 0. The number 2 is still the number 2, and 1 over infinity gets me 0. So I now have infinity being divided by 2. Okay, what is infinity if you divide it by 2?
Still infinity.
Right, so doesn't this one diverge? Agreed? If the limit's infinite, it diverges. Now I said there's 3, so let me do the last situation. Right, there's a guy. And as always, I'm going to try and find what its limit is. Okay, biggest power on the numerator is n cubed. Biggest power on the bottom, the denominator, is n to the 6. You know my rule about decisions. Tell me which one I should use, n cubed or n6.
N cubed.
Okay. Let's see what we get then. If you divide this by n cubed, you get a 4. You divide this by n cubed, you get 2n squared. You divide that number and you get 1 over n cubed. You divide this by n cubed and you still get 5n cubed. And you divide this by n cubed, you get 1 over n squared. Are we comfortable about the pieces, where they all come from? Right. Now the brute force part kicks in. 4 plus 2 over infinity squared plus 1 over infinity cubed. And on the bottom, 5 lots of infinity cubed plus 1 over infinity squared. Okay, 2 over infinity is still 0, 1 over infinity is still 0, so you end up with 4 plus 0 plus 0. And 5 infinity cubes is infinite plus a 0. And so we now get 4 on the top, numerator, infinity on the bottom. And what does 4 over infinity get you?
0.
So this one converges to 0. So can you see that you can get a converge to 0, a converge to a number, or a diverge? And doesn't this method find all 3 situations? Right, you get a number, you get a 0, and you get a diverge of some kind, right, and infinite. quick pause here. Are we good? Do you feel comfortable about this process? Right. So we've looked at brute force, which is basically just this bit, isn't it? It's like this method just uses brute force as part of its process, right? Next fella in my list of techniques is L'Hopital. You would use L'Hopital when you are being asked to find the limit of a sequence and it has, what would it have? Things like 2 to the power of n in it, or e to the n or something like that. So let me do an e to the n over n squared, right? That would be a good candidate for L'Hopital. Would you agree you can't really divide the top and bottom by n squared here? It's not going to help you much at all, right? So we know that's not good. Well, what about brute force? Well, you have a problem. Isn't e to the infinity, and isn't infinity squared infinity? Don't you just have an infinity over infinity thing? That doesn't work. So we're going to do the limit as n tends to infinity. And we are going to take this guy and put a little L to tell people we're doing L'Hopital. And to remind you how that works, you you differentiate the top and the bottom separately. And then you try, if you can, to get an answer. Well, if I plug infinity here and infinity here, don't I still get left with infinity over infinity? It's called an indeterminate form when that happens. So it ain't working. So what do you do if you do L'Hopital once and it isn't working? You haven't got an answer yet.
Keep repeating, right?
Yeah, you just keep doing it until, you know, it coughs up the answer for you. So differentiate the top, differentiate the bottom. Now I think we're getting somewhere. E to the infinity over 2. Well, e to the power of infinity is infinitely large, and dividing something that is infinitely large, you get that guy, right? And so it diverges. Are you comfortable with the L'Hopital thing? Right. Do it 2 or 3 times if you have to. Hopefully you only need to do it once. Now there is a lot of overlap. What do I mean by that? It means that you could have done these questions with L'Hopital as well, couldn't you?
Yes.
Yeah. But very often polynomials don't always behave well. You know, if there was an n to the 7 somewhere, wouldn't you have to do L'Hopital about 7 times before you could get an answer? And wouldn't that just get big and long and boring, right? So this is a cleaner technique. But, you know, I don't expect to see a lot, but it can happen. The last one I'm talking about is called the relative rate of increase. Now, to be able to do this one, you have to know which functions get bigger faster. The biggest thing in the world, as far as you're concerned, is n to the power of n. Can you imagine how quickly that guy gets big? How quickly it becomes infinite, right? Do you know, for instance, if n is just 100, right? Not massive, right? 100. It's 100 to the power of 100. You know that's got an awful lot of zeros, right? That is a huge number. The next guy, so I'm starting from the ones that get big really fast, is n factorial. Right, 10 factorial is pretty big. 100 factorial will break your calculator. If you try to do it in your calculator, it'll just say error. That's how big it is. What do you think is going to be next in the list of getting big quickly? Any ideas for I write it?
Constant to the power of n.
4 to the n, 10 to the n, 7 to the n. I'm just going to put in 2 to the n as a placeholder. Because won't 3 to the n beat a 2 to the n, right? And 10 to the n will beat both of them, right? But anything to the power of n is the next fastest guy in the world, right? As long as that number is, a whole number, right? Then you get powers. I'm only putting n squared in as a placeholder, right? But won't n squared beat n's, but won't n to the 4 beat n squared, right? So in that, there's a whole family of answers. And we're pretty darn close to the only ones that we need to memorize or remember. After you do things like n squared, right? N would be the next one down. That would belong to that family. Oh, God, I almost forgot. Try that again with n's. Square roots of n become infinite, don't they? Don't they just take a heck of a long time? Do you know the square root of 1,000,000 is only 1,000? I mean, it's getting bigger, but it takes a long time. That thing there, I'll write it again, is square roots, cube roots, 4/3. Now the guy was 1. Do you know the log of n gets slower? It's like the slowest one in time, right? It doesn't go to infinity very big. If I pretend it's base 10 for a minute, do you know that the natural log of 1,000,000 is just 6? You're talking base 10. Right, we agree it ain't getting big anytime soon. So how does this thing called the relative rate increase work? Well, if you're being asked to find the limit of a sequence, and it's typically going to have to be a fraction, you're going to have a guy in the top and you're going to have a guy in the bottom, right? And the guy in the top is going to be one of these, and the guy in the bottom is also going to be one of these. And you can figure out whether the answer is going to be 0 or diverges, because that's all you get, right? One of them beats the heck out of it and zooms off to infinity, right? Or, it kills the thing and kills it down to 0. So you're not going to get equals 10 or 20 here. You're going to get 0 as the limit or infinity as the limit. So let's give you an example. How you tell. You tell by looking at which one of those two gets bigger quickest. Which one is it? That one, agreed? That means that the bottom is massively big in relation to the top number, right? When you get to, towards infinity. And so if that's massively big, your limit is 0. Does that make sense? Something that's big being divided by something that's massively big is going to kill it, right? The bottom's going to make it like 2 billion over American debt, right? The American debt's going to win, right? It's trillions. The 2 billion sounds like a lot, but it ain't a lot when you think of it as trillions. So basically, you're going to do a kind of whichever one of these guys, right, is the biggest, tells you what it's going to be like. So for instance, n to the n over n factorial. Which is the biggest? Obviously n to the n, right? So isn't that going to take over? Isn't that going to be the dominant feature for this fraction? So won't a massively big thing, even if you just divide it by a big thing, isn't it still going to be infinitely large? And so that's the situation where you get infinity. So basically, if the big guy is on the bottom, you get 0. And if the big guy is in the top, you get infinity. Does that make sense? Do you think it matters if I stick a 3 there and a 2 there? No. Would you agree that 3 of them and 2 of them don't make any difference, right? So if somebody says 3 n to the n over 2 million n factorial, it's still going to be infinite. a single constant doesn't really make a much real difference in the big scheme of things. You can even mix and match the same guy. So for instance, what would that get you? Well, who's the biggest? And if he's on the bottom, the answer's 0. And if he's on the top, the answer's infinite. Who's the biggest between 2 to the n and 5 to the n?
5n.
Right, and it's on the bottom, agreed? And if it's on the bottom, what's the limit going to be then?
0.
0. Now let's do a few cosmetic tweaks to this. 2 to the power of n plus 1 over 5 to the power of n minus 7. Doesn't matter. Doesn't matter one iota. Isn't 5 to the power always going to be a 2 to the power? Isn't the answer still going to be 0? You're not always going to get answers that are clean, right? They're not always going to be 2 to the n and 5 to the n. Aren't you going to get 2 to the n plus 1 and 5 to the n minus 7, right? There's going to be little tweaks to it. But the cosmetics don't care. That guy is still going to beat that guy. That guy is massively bigger than that. Even although you're knocking a few terms off, by the time you get to infinity, doesn't 7 not matter one bit? Really doesn't. Are we good? So I'm going to zoom over and look at some of these homework questions. And hopefully you should be able to just look at a lot of them at least and tell me what the limit would be without getting too caught up in, you know, the math, because once you've done a few of them, you kind of get used to them and you know what it's going to be. What would the limit in 14 be?
0.
Yeah, couldn't you do that by brute force? Now, in homework, you're probably just going to go 0 and it'll be right. But can I strongly suggest that you make sure that you know how to prove it to me? Because when you do the midterm, writing down the answer as 0 is no good, because I could get the answer 0 lots of ways. Couldn't I just use my calculator and figure out what the answer was, you know, based on limits, in the sense, well, when n is 1,000,000, it's 0.0006, so it's probably 0, right? That kind of trick. Nah. So this method, you know, the divide top and bottom, L'Hopital, whatever method we're using, even if we're doing the last method, you should at least be telling me something about why you came up with your conclusion. Okay, a little bit harder, but you should be able to tell me the answer to 15.
3.
Agreed? You all agree? 16? Or at least my 16.
Infinity.
Agreed, so it diverges. When it doesn't work, right, when it's infinite, what you do is you actually type in capitals, diverges, right? That, you know, so don't type in infinity, because WebAssign might just say you're wrong. Oh, I like this one. Couldn't you divide the top and bottom by square root of n? So
Indeed,
that's a
you
version.
can do it.
Yeah. Wouldn't the answer be 4?
That would end up become 4, I would assume.
It would be. You're right. Okay. 19 is the relative strength one, right? The relative rate of increase. Okay. 2 to the n on the top. Do you think that 1 plus makes any difference to the guy in the bottom? Right. So haven't you got 2 to the n on the top and then 9 to the n on the bottom? Okay. What's the limit going to be in that situation?
0.
Big fat 0. I'll leave you. That one's fun. What technique should you use for that answer? Because I don't expect you to tell me the answer, but what technique should you use to do that, guy? We've talked about 4 methods today. One of them is the go-to method for that weird looking fella.
Relative rate of increase.
You'd get a problem with that. I understand why you're doing it, but I wouldn't do it for this one. A lot of the times I would, but not this time.
How about Lobato?
Yeah, do
L'Hopital.
L'Hopital on it. Right. Well, what's good about L'Hopital? Won't the logs disappear and it'll turn into some 1 over n and 1 over 3n, which I believe the answer is either 3 or a third. I'm not quite sure because I haven't been able to do it totally in my head. This guy here. Any suggestions for the method?
This is still the L'Hopital rule.
Yeah. Wouldn't you just have to rewrite it as n squared on the top over e to the positive 3n on the bottom? And if you did a couple of L'Hopitals, the answer I believe would be 0. Not all questions fit neatly into the boxes I gave you. So this one I think qualifies as not fitting nicely into the box. Algebraically, is there any idea what you might do here? Because the way it's written right now is no good to nobody.
We're dealing with logs, so when you subtract logs, you can divide them.
Okay, I like your thought. Hold that thought because it's good. I'm just going to write down what you just said and let's take it slowly so that those who are not quite sure why you did what you did. Right, so that's original. And you went and said quite correctly that that divided by that. So that's what we're looking at. It's a good start. It doesn't fit well into the boxes, but it can be done. Where are we off to now?
You cancel out the n's.
Cancel, yeah, in a way, but I hope by cancel you mean this. In other words, just split it into 2 pieces. Now, at this point, can't we use brute force?
Yes.
And the answer ends up being the natural log of 1 plus 0, which is the natural log of 1, and the natural log of 1 is 0. So after all that hard work, the answer was 0. Now, I'm not saying that's the only way you could do that question, but for me, that worked. That worked, right? So not everything works into a pretty answer. Let's return, because I've seen a couple of more cool ones. I love these questions, just to get your brain working. Right, let's look at this guy, make this bigger. Right. What's the limit? You should be able to tell me.
Zero.
Correct. What was your thought process?
Cosine doesn't really go beyond 1 or -1.
Right.
While the 3 to the n power is constantly increasing.
Correct. Good way. Now, if you were doing that in a test, you might have to write that sentence down, because sometimes you can't really do algebra to show what you're doing in your head, but at least you can say in English what you're doing in your head, and what you phrased there makes perfect sense to me. Technically speaking, if you wanted to be formal, you could do a technique called the sandwich method, right? But what you said is good. 25 is a really cool question. Tell me the method, nothing else. What method would you use to get 25? Sneaky one, isn't it? Any ideas? Last few seconds. Rather not tell you.
Could you just brute force it? Because
Well,
sine
yeah.
is going to be confined to 1 and -1, but the n over 3
well,
isn't.
I like your logic is pretty good, but unfortunately it's a little bit flawed, and I'll tell you why. The sine of 3 over infinity becomes a sine of 0, and the sine of 0 is 0. And infinity over 3 is infinity, and infinity times 0 is not a good place to be, right? Now, if the sine thing had been 1, that would have been a perfect place to go, right? In fact, if I changed that to the cosine of 3 over n, wouldn't that strategy work perfectly well? So, but I like thinking. I don't mind people, you know, just having a shot and, you know, letting their brain run and see what happens, because very often students come up with better ideas than I do when they do that. Right, this is the guy. I am going to do some weird surgery on this. Do you know that guy's the same as this guy? Isn't it? Now that I've written it like that, have you got an idea of what technique I'm going to use?
L'Hopital?
I'm going to use L'Hopital. Check it out. You might say, well, that's not going to do any good. Trust me, it does a lot of good. Because what you're going to end up with is the cosine of 3 over n, which becomes the cosine of 3 over infinity. The cosine is 0. The answer is going to be 1. Pretty impressive. Almost done with these guys, but still some good ones left over. I'm going to keep 26 to the end, because in question 26, I'm going to tell you something that's true, and you're just going to believe me. Right? That's the best I can say, but that's for the future. I think 27 is very similar to a question we did earlier. And aren't you going to combine them as a log of the first guy divided by the second? And it worked out great. I think you end up with a log of 2 when you're finished. 28 has no formula. So all bets are off here. You just got to tell me the answer. Does this sequence converge or diverge? I don't need to know more than that. Does it converge or does it diverge?
Converge.
Interesting. You've got to back it up if you're going to do it.
It's kind of a similar pattern to sine. So just since it's constantly alternating between 2 points, just the gaps are getting wider. That would be diverges.
That's a good argument for why it's a diverge. Now, I can understand why you might say converge, because wouldn't there be more and more zeros before you get the next 2? But isn't there always going to be a 2? Right, and that's the kicker in the tail that makes it a diverge, right? But there's no proof to that. Would you agree? You just think it through, and your logic hopefully comes
So
up with
wouldn't
that.
that make 2 the limit? Because it's never gonna go past that number.
Well, yeah, but what about 0? Couldn't 0 be the limit? And if you've got 2 choices, the answer is diverges. Remember, diverges can be, I'm bouncing 1 minus 1, 1 minus 1. That counts as a diverge. Well, isn't 0 to 2, 0 to 2, 0 to 2 also counts as a diverge? So for that same reason, I would say it still counts as a diverge. Oh, there's our friend. Can you see an example of the relative growth rate one? Okay, so everybody agree it's infinite, so it's divergent.
Agreed.
What about 30? What's the limit of that going to be?
0.
Isn't that the relative growth rate situation again? And I promised you one answer that you're going to have to trust me. So here it goes. You won't be able to get this unless you've seen it somewhere before. This sequence, if you find its limit as n tends to infinity, and I'm going to show you the general version of this. So if you ever get a sequence that looks like this, 1 plus a number over n raised to a multiple of n, right? So in this case, it was A was 4, technically B is 1. This thing has the limit e to the power of a b. And I'm telling you that's what it is. So what would this one be? Well, wouldn't it be 4 times 1? Wouldn't this one be e to the power of 4? Now, if you want that to be proved, ask me about week 8 and I will prove it, because by week 8, you'll have the math that will be able to do that, right? But right now, we ain't got that math.
This looks very similar to a population. I was just saying it looks similar to a population formula.
What, one of the population model? Oh, have you graphed it?
I've graphed them before. But
Yeah. I didn't think of it that way, but yeah. The population in this case levels off at whatever e to the power of 4 is.
yeah.
That could be a population model. We are done for this section. That's kind of fun, isn't it? We've figured out, hopefully at least, how to do limits of sequences and a few other bits and pieces. So slowly moving on to the next section. So that's why I'm kind of running around here and getting myself prepared. We're now going to start 11.2, which is the second and final section for this week. And I've got the thing up and running. I should have. Come on, where are you? There we go. Yeah, that's good. So, kind of giving you an intro today. Try and get as much done as I can, but there's an awful lot in this section. This is section 11.2, and we're going to be dealing with the introduction, at least, to things that are called series. Now, stuff you need to know before we get into series. Let's talk about a thing called sigma notation, because that gets used an awful lot. Sigma notation uses that big Greek letter. It's the capital sigma, right? You know, like the little baby sigma looks like that. If you've done statistics, capital sigma looks like that. And it has a number of features. The first thing is the shape. So if you ever see that, you know that you're going to be adding things together, sigma for some. I'm going to put n equals 1 to n equals infinity. And I'm going to be putting in some expression. That is an example of sigma notation. It's a very concise way of getting you to add up an infinite number of things. So you're going to start at 1 and you're going to finish at the end of the universe. And what you're going to add up, you're going to add up whatever 1 over n squared is. So when n is 1, you get 1 over 1 squared, right? And then 1 over 2 squared, then 1 over 3 squared, and then 1 over 4 squared, ... forever. Are you comfortable with how sigma notation gets you in a very concise way to add up an infinite number of things, right? So far, so good. If I have a sequence, an, it would be a1, comma a2, comma a3, comma a4, right? So that would be every sequence in the world could be written like that, right? Because I haven't given you a formula. It represents pretty much every. So this guy here is a sequence. If you take any sequence and you add all its terms together, right? That's what it would look like in sigma. And we'll call it S. That guy there is a series. So a series is a single number or infinity, right? A single thing that you get when you add a sequence together. Now, you might think that if you add up an infinite number of things together, that the answer has to be infinite, right? Because you're adding an infinite number of things. But that logic isn't correct. Sometimes it's right, right? There are lots of cases you add it up and the answer is infinitely large, right? And when that happens, we just say that the series S diverges. So that's what you would say if this thing added up to infinity, right? That can happen, but it doesn't need to. So I'm going to show you a sequence that when you add it up, right, if you make a series out of it, it actually adds up to a fixed amount. You're ready to be amazed? Infinite things added up to a fixed number. So I'm going to have as my sequence this guy here. One half to the power of n minus 1. Now, if you plug in, right, there's A1, there's A2, there's A3. I guess I'll need to go to A4, right? Dot, 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 dot. If you plug in 1, you get a half to the power of 0 is 1. Then you get a half. Then you get a quarter. Then you get an eighth forever. Are you comfortable? That's what that sequence would look like. Right? So far, so good. Now, I'm going to find a series by adding these all together. I could use sigma notation, but I'm not going to. In this case, it makes it easier to see why this adds up to something. Now, I'm making the assumption that it adds up to a thing called capital S, right? S is just a placeholder, right, for the answer, right? It's a single value, 42, a half, infinity, whatever it's going to be, right? So far, so good, right? Now, I am going to take this guy here, right? And I'm going to multiply it by a half. So I'm now going to write down what a half of this is. Right, now if you take all of these terms and you multiply them by a half, don't you get 1 times a half, sorry, a half times 1, a half times a half times the next one, and that one. Would you agree that that's what this would look like? When you basically get the same terms, just one different, right? Because half of that gets you 1. So they're kind of diagonal. And the reason I'm lining them up this way, I could have just shifted that along, is the next step. If you take this series and you take this series and you take the top one and you subtract the bottom one from it, something really amazing happens. Doesn't everybody here get killed? Right, top guy, subtract the bottom. Only thing is left is the first term, 1. You with me so far? Now, S, take away a half S, isn't that 1/2 S? Do you agree algebraically? X, take away a half an X is half an X, right? Algebraically, that's valid. So what does S equal? Right? How did you get? Think solving equations. Forget about sequences. 2, agreed. Have I now proved to you that that thing there, even although you're adding an infinite number of things together, the answer is 2. Isn't that kind of interesting? That you can add up an infinite number of things and the answer is still 2. Right? They add up to 2. Now, if I'm being really pernickety about it, it's not that it adds up to 2, but its limit adds up to 2. That's me just being a bit lawyer-esque, right? Okay. But it's cool. Aren't there going to be a lot of series out there that just add up to infinity? Agreed? And there are going to be a few, probably less of them, that add up to a number that you can actually live with, right? They add up to a finite value. You wouldn't be too surprised to know that mathematicians are much more interested in the ones that add up to a number than the ones that are infinitely big, right? Because they're pretty much, you can't do much with them, right? Because, well, they add up to infinity and you're not going to get anything out of that. A lot of banking and financing, where you put money in and then you get interest on the interest on the interest on the interest, you know, those kind of snowball things. A lot of them can be written down in this term, right, using this kind of technique, and therefore you can actually figure out what something would be equal to if you just left it there forever, right? So it's kind of fun, I think. It's kind of fun. So that was our intro to a series. I haven't quite finished because there's a guy called a partial sum. So let's take, as my example, let's take this series. And this time I'm just going to pick something pretty boring like that. That's a series. Excuse me. That is a series. It actually does converge to something. Not that you need to know it for what I'm about to do. But you can use any letter you like when you do a series. Mathematically, for instance, isn't k equals 1 to infinity of k plus 1 over k cubed? Would you agree that mathematically they are exactly the same things? They're just using different variables. So don't get too caught up on the n thing. I'm going to use that version for partial sums. So there's a guy called a partial sum. And every series has one. Well, has lots of them. And it's described like this. Essentially, isn't a partial sum what you get when you add the first n terms of a series, right? Or a series, I should say, right? If you add up the first n terms, does that make sense? So in this case here, if I asked you to do S3, wouldn't you be talking about, and now we can return to the n's if you like, n equals 1 to 3 of n plus 1 over n cubed. Well, that would be what you would get if you took the first term and then you added the second term and then you added third term. And whatever that adds up to, that's partial sum S3. Special case. Won't partial sum S1 just be the first term? Which in this case happens to be 2. Won't S2 be what you get if you add the first term and the second term? So it'd be basically those two guys. So that would be 2 plus 3x. And that's 16, so that'd be 19x. And then if I do one more, which is S3, it would be that answer plus 4 27s. I'm not doing that in my head. So that guy plus the next term after it. So 19/8 plus 4 27s. And hopefully that'll turn into a fraction. And S3 ends up being that fella. Now, if I wanted to, couldn't I do S4, S5, S6x, the 90th partial sum? Now, what happens then is, can you imagine that you start off with a sequence, which is that guy? And then can't you find the partial sums? But if you write the partial sums as its own sequence, I know that's kind of sounds like a snake eating its tail. Can't the partial sums create a sequence? S1's the first term in the sequence, S2 is the second term, S3, S4, whatever. So you've got this, you start with a sequence, you create all the partial sums, which in turn generate a sequence of partial sums. Now you might think, why are we doing this? Rather, you start with a sequence, you create this series, you then figure out what the partial sums are to create yet another sequence. If you wanted to know, does something add up, right? Does this series, right? What you get when you add them all up, does it work? Couldn't you find out what the partial sums are? And if the limit as n tends to infinity of the partial sums is a number, let's say 10, doesn't that make S, the series, add up to 10? Does the logic of that make sense? That if the sequence of partial sums has a limit as n goes to infinity of, say, 10 or any number, doesn't that mean the series converges to that same number, 10? So that's a kind of roundabout way in which we sometimes have to do, or we try and do, to find out what the limit of a particular series is, right? What does it add up to? Okay. And to finish, I'm going to tell you a little story. I think I'll do it over here. The Greeks were really good mathematicians. I mean, they were the kind of mathematicians who really created an awful lot of the math that, at least up to the Middle Ages, was basically the only math around, right? That's how good it was, right? It lasted 1,000+ years. And they actually knew a little bit about sequences and series, but they got it wrong. And the way that they proved or tried to prove it was this story. Can't remember what the Greek guy is, but I want you to imagine that's a frog. I know it doesn't look like a frog. I'll give it 2 eyes there. Does it look more like a frog? Nah, forget it. That's a frog, right? And this frog wanted to get to the water, and the water was 2, whatever the Greeks units are, 2 miles, or not, 2 meters away, right? And this frog took a jump, and it had the property that every time it jumped, it only jumped half what it jumped before. So the first jump was 1 meter, right? And then the next jump was a half a meter. And then the next jump was half of that, a quarter meter. And then the next jump was a half of that, an eighth meter. So if you wanted to know how far the frog traveled, aren't you basically just adding up this guy? Now, we did some math there, and we got the answer 2. And the Greeks done very similar math, and they got the answer 2, or at least some of the mathematicians did. And then other mathematicians laughed at them and said, your math has to be wrong. And they did this argument. Theoretically, isn't that frog going to keep jumping forever? So theoretically, that frog can never reach water. So that frog can never be 2 meters in total. Isn't it always going to be just a little bit shy of 2 meters? And so that kind of stopped them looking at limits, because they always came up with this fallacy that, okay, you said it adds up to 2, but I can show you in common sense, whatever you want to call it, it can never be 2, right? The frog's always going to be just a little bit shy, isn't it? And no matter how much it jumps, it's still going to be a little bit less, but still shy. And that's why when I said, if I was being lawyer-esque, isn't the limit of this 2? Rather than me really saying it's definitely 2. And that subtle difference is why we got a kind of head start on the Greeks. They didn't like certain things, and they got kind of arrogant because they were that good, that if they didn't think it was true, then it couldn't possibly be true. Instead of them saying, well, maybe there's another way of looking at this that might be useful. Side issue, they never liked square root of 2. They couldn't understand it because the Greeks believed all numbers were fractions. And the square root of 2, it was basically, I think it was called circumferencing the square or something, a name like that, which basically was trying to find the radius of a square, the radius of a circle connected to a square. Really bugged the heck out of them. And who knows what they would have discovered if they hadn't came to that brick wall. So you lot are going, nice fresh minds. So I can tell you anything and you're going to believe it, right? Well, anything mathematical, let's be honest, right? But never let something, because someone gives you a plausible argument for why it's not true. Can you imagine what a Greek person would have done if you told them about the square root of -1? Well, first, they don't like square roots, right? But if you could go over that hurdle, what about the square root of -1? Can you see that if you put barriers and you say, well, that's the end of that, you can't do that, then aren't you not giving yourself the chance of growing?